It doesn't show
No.
all.
Okay,
Mm-mm.
recording now. Thank you. Sorry. Thank you for reminding me. Always good for the reminder. So we are now in week number 11. So this is going to be lecture number 21. And we are starting something which we have not yet done before, which is actually considering two variables at the same time and whether or not those two variables have any relationship between them. We spent a lot of time on basics of probability and understanding, likelihood of events and the various rules associated with them. We spent a lot of time looking at a single variable of data, the mean, the median, the mode, the standard deviation, the interquartile range, right? All the various ways of analyzing a single variable. And now we're getting into the heart of this semester, or really, I guess, the culmination of the semester, the last few chapters, which will be analyzing two variables at the same time. And what we have here in front of us is a scatter plot. What is a scatter plot? Well, I'll kind of give you a hand wavy definition in just a second, although it's, I think, somewhat self-explanatory. But what we have here is a plot listing lots and lots of countries throughout the world. And if you'll notice that the x-axis and the y-axis, the horizontal and the vertical axis here, are quantitative in nature, right? There's numerical values where averaging and mathematical operations make sense. So on the x-axis, we have the years of schooling that a girl can expect to receive. This axis goes from 1 to 20, technically, I guess, 0 to 20. And we also have on the y-axis, the vertical axis, the projected total fertility rate. How many children per woman in these countries, of course, again, on average. David, good to see you. I'll mark you as on time since we basically just started.
Okay.
So you're welcome. So every one of these dots, right? The first question, what does each dot on this scatter plot represent? Every one of these dots is a country, right? You have Nigeria on top, you have Afghanistan, which is a country, in Chad, and all these different countries. This is from 2011. And I know that countries don't change names necessarily on a daily or weekly basis, but it is theoretically possible that in the last 9 years, some of these countries may have come into or out of existence. I don't know, but let's assume that they're all still around. Each one of these countries actually has 3 variables in this scatter plot. So even though the question says, what are the 2 variables plotted for each dot? Really, it's 3 variables, but only 2 of them are quantitative. Okay, the 2 quantitative variables are the x-axis, the years of schooling, and the y-axis, which is the projected total fertility rate. But there is a 3rd variable here, and that's a categorical variable. Could anyone tell me, based upon this scatter plot, what that 3rd variable might be labeled as? Because there is a 3rd distinguishing feature besides just the years of schooling and the projected total fertility rate. Anyone see it? Hopefully you're not colorblind. If you are, you might have a little trouble here. But does anyone see the 3rd?
The colors?
The colors. What do the colors represent? They're not just randomly thrown in different colors. Each color means something. So where on this graph do they tell me what each color represents?
It's like a certain region.
Yeah, excellent.
Top right.
Yeah, the top right tells me that the various colors represent different regions. Why might I want to distinguish different regions? Well, usually, a statistician just does the statistics, but there's also the analysis afterwards, right? We want to make predictions. We want to infer things. We want to see if there's relationships between variables. Perhaps by dividing it into regions, some distinguishing feature might present itself that we might not see otherwise. And the more experienced you are as a statistician, the more likely you are to recognize, which variables matter versus which ones don't, and how to represent them. That being said, we're really going to focus more on the mathematical ones, the quantitative variables here. I just want to point out that such variables exist. Now, so again, the middle question. So what are the two variables? What are the two quantitative variables plotted for each dot? Who wants to venture a guess? Or not a guess, a definitive answer. What are the two quantitative variables plotted for each dot?
Projected total fertility rate and years of schooling girls can expect to receive.
Fantastic, Laura, you're a rock star. So how would you describe the relationship between these two variables?
The relationship.
I asked you first.
Oh.
How would you describe the relationship between these two variables? Would you say, well, based upon the scatter plot, there's no connection whatsoever? Would that be a reasonable conclusion based upon what we're looking at here?
There's no relationship?
Well, I'm asking, would it be safe to say, based upon the scatter plot, that there's no relationship between them?
There is a relationship.
I would think there is a relationship.
Well, that's what I'm asking. How would you describe said relationship, assuming there is one? How would you describe it?
The more schooling. Sorry, go ahead.
It's all right.
Go.
Ladies first.
I was just saying, the more schooling, you're not going to have more kids or something.
Okay, so there definitely seems to be this relationship that the more years of schooling that a girl can expect to receive on average, the lower projected total fertility rate. We definitely see this downward trend, right? As we go further to the right, the graph goes down. Would you agree with that? Would everyone agree with that? Okay, so as we're going to say in this chapter, we would say that they are negatively correlated. The negative is essentially coming from the fact that it goes down, okay? Or it's decreasing. Usually we would use the word negatively correlated if we're dealing with a linear relationship. And are we dealing with a linear relationship here? Does there look in general to be taking into account the fact that in real life, nothing's ever perfect? Does it seem overall that there is a linear or more of a curved relationship between these variables?
Linear.
It certainly seems linear. In fact, they even drew a line, right? There's a line that's kind of drawn right through the graph, what we call a best fit line. Although we're not going to talk about that in this chapter, that's going to come later. But there seems to be a line that's through the graph that kind of represents the linearity of it. Okay, and we're going to see that there's a few features of a graph that we're going to be focusing on. One of them is whether it's negative or positive, and the other one is whether it's linear or not. And then how strong that linear relationship is. We'll get to that in a few minutes. Okay. So first, let's kind of grasp onto this word linear that we're using here. When you're in algebra, in basic algebra, and you hear the word linear, right? What are the first four letters of the word linear? What does that spell? The first four letters, it spells line. Okay, when you think of linear in algebra, we think of points on a line, right? All the points are perfectly correlated in the sense that they all fall on exactly the same line. But in real life, there's always going to be variation. No matter how, I don't want to say always. I mean, there's almost always going to be variation. So even though things could be linearly correlated in the sense that it's a linear relationship, we're happy enough saying that they kind of cluster around the line, even if they don't fall exactly on the line. So in this class, when we talk about linear, at least in this chapter, what we mean is a relationship for which a line drawn through really makes sense. And of course, then we're going to want to figure out how to find that line. But for now, don't say, oh, this is not linear. They don't all fall on a line. No, that's in algebra. In statistics, we're happy enough even in a situation like this. Okay, does that make sense so far? Any questions from anyone? All right. So here we have another scatter plot, a plot of dots. Notice again that we are plotting a relationship between two quantitative variables. The x-axis and the y-axis both have to be quantitative. But at the same time, we're again throwing in a categorical variable. How do I know there's a categorical variable here? What gives it away?
A dollar sign.
Well, the dollar sign is our units, correct? And units usually indicate a quantitative variable. And in fact, the x-axis is quantitative in that regard. But so yeah, it's the colors again. right? It's the colors again, the difference between the advanced economies, the emerging markets, and developing economies in terms of this particular scatter plot. Would you say when you look at the colors that the colors kind of group together? Or are they just all over the place and colors don't seem to matter at all?
They group together?
They do seem to group together, right? So whoever made this chart kind of feels that the colors mattered and threw the colors in there to kind of give you an overall idea, not just of the relationship between the quantitative variables, which is what, you know, we're plotting, but also to say, notice that all the points, all the advanced economies kind of have similar features, and the emerging markets kind of have similar features, and the developing economies kind of have similar features. Now they drew a curve through this scatter plot. Is that a line that they drew, or is that a non-line? Is it a true curve, or is that a line? What would you say based upon just looking at it?
True curve.
It's a curve, right? This is not a line, right? It goes up like this, right? So this is a non-linear relationship. Nevertheless, it's still a positive relationship because it's still going up as we go left to right, correct? Here's another example of a non-linear relationship that hopefully you all agree with. One of my favorite examples, suppose you were to plot heights of children as a function of their age. So in other words, you start at birth, and then the x-axis is how old they are, and then the y-axis is how tall they are. Okay, would you say that there's a positive relationship between age and height? As people get older, do they get taller?
Yes.
Would you say that's a linear relationship or a curved relationship?
A curve, because old people get shorter.
Old people do get shorter, that's true. And in the middle age, you kind of stagnate and kind of just stick around, correct? But imagine you only looked at like 0 to 2, and you graphed height versus age for 0 to 2, and then you just kind of assume that it kept on going that way. You would predict that like a 90-year-old is like 800 feet tall, right? Because the graph would just whoop, go straight up, and of course that makes no sense, right? So it's very important never to assume, just because you have linear data, never assume that that trend continues indefinitely. We don't want to extrapolate. We don't want to apply our trend to outside the data, because who knows if the trend really continues or not. You only want to interpolate. You only want to use the trend to conclude things within the data, okay? Here, we're going from 0 to 60,000. That's this the GDP per capita, some economic modality factor. And then here on the y-axis is people's percentages for what percent say, or basically, well, let's just read it because it's very wordy. Life satisfaction. Okay, so in other words, who is satisfied with where their life is at on a scale of 1 to 10 or 0 to 10? Okay, on a ladder of life from 0 to 10, on which step do you stand at the present time? How many say 7? How many say 8? How many say 9? Or how many say 10? What percent would say 7 to 10? So as you can see here, the general trend is that for countries with developing economies, okay, very poor countries in the grand scheme of things, their satisfaction of life as a general is pretty low. And as the GDP rises, as the economic strength of the country increases, usually the quality of life or satisfaction of life increases as well, but only up until a point, right? Once you reach a certain point, then it kind of just stagnates. And if you were a sociologist or someone who studied this kind of things, you might come up with all types of reasons why. I'm a statistician. I don't care about this kind of things. I just look at the numbers and try to understand what's going on. Of course, you always want to have an explanation for why things are true. That way you can identify outliers, or you can identify things that don't make sense. But in this case, my understanding of economics is so weak that I don't really have an explanation for this, other than the fact that I guess, you know, once you have enough money, who really cares if you have a little more money? You know, right? You make enough, you're a billionaire. No, okay, now I'm twice a billionaire. Did it really help? I don't know. People might be happy with a given amount, They can afford everything, and everything after that's just icing on the cake, right? Now they have more money in the bank, but they're not really getting anything from life more just because they have more. Maybe that's something to do with it. I don't know. Let's keep going. So let's talk about strength and trends. Okay, so when we talk about these scatter plots, these plots of data that are scattered all over the place, we're going to talk about essentially 4 things. Okay, and the first one is whether it is linear or not. When you look at it, do you see the dots kind of congregating about a line? Now, in the top left one, would you agree, hopefully, because this one is pretty clear cut, but would you agree that the top left one is a linear relationship?
Yes.
Yes.
Okay,
Yes.
yeah, that one seems like a no-brainer, correct? Now, if you go to the bottom right, would you say that's a linear relationship?
Yes.
Okay, so it's not falling perfectly on a line, but remember this is stats. So as long as it clusters, it's good enough, right? And we have this linear relationship. Which one would you say of the remaining 4 is the next strongest when I use the word strength as how close to a line it really is?
Bottom left.
Okay, bottom left again, I would agree, is the next strongest. Okay, which one after that?
Middle bottom?
Okay, I'm with you so far. Middle bottom, I love it. How about which one next?
Middle top?
Okay, middle top. And how about the last one? When I look at the last one, I mean, even the middle top, like when I look at the middle top, I kind of can imagine a line going upwards. When I look at the top right, I don't see anything. Right? I just kind of see a blob. What's that test called? The Rorschach test or something? Anyone know what I'm talking about? You know, where they just kind of just put ink on a page and it's just like a blob of points. I don't know, whatever it's called. I just see nonsense there, right? I just see what's it called? Rorschach. Okay, so I just see like point. I don't see any relationship there at all. So the top one, top left, very strongly linear. Bottom right, even this, well, this one, by the way, is perfectly linear. It's a step better than strong. This is perfectly linear. This one here, I would say, is strongly linear. Then we have moderate strong, moderate, weak, and then non-existent. So we have these, you know, we have this spectrum of qualitative descriptions of how strong the linear is. Luckily, we don't have to rely upon our eyes because we're going to have a mathematical way of determining whether or not it's strong or moderate or weak or non-existent. Be aware that I can show you the same graph and zoom in or not zoom in. So give it to you at 2 different scales and you might come to 2 completely different opinions about how strong it is. The eye is very easily deceived in that regard, which is why we like to have mathematical formulas, because you can't deceive math, right? Math is the ultimate. I got no word here. I'm not sure what word it would be, but you know, if you do the math, you get the definitive answer, no arguing. So that's what's great about math. All right. So very strong all the way to extremely weak or even non-existent. Now, after we decide whether it's linear and how strong it is, the next feature that we might care about is whether it's a positive relationship or a negative relationship. Is it going up as we look left to right, or is it going down as we look left to right? So the top left, positive or negative?
Positive.
Positive. Okay. Top middle, positive or negative?
Positive.
Positive.
Okay. Top right, positive or negative?
Positive.
Well, I don't know. We already spoke about that one. I don't see anything.
Scattered.
I don't
We
see.
don't know.
I don't see nothing there. I see 0. I see nothing. Bottom left,
Negative.
negative. Bottom middle,
Positive.
Positive.
positive. Bottom right,
Negative.
negative. Fantastic. All right. So Hershey Park, which I've actually been to back when I was in my younger days. Hershey Park in Pennsylvania contains some of the most famous roller coasters in the eastern United States. Now, I'm from Chicago, so we had our own roller coaster park in Chicago. Anyone know what it is? Anyone know the big roller coaster park near Chicago? What is it?
Six Flags.
Six Flags, right? I think Six Flags is the name of the company, because I think there's Six Flags in a lot of places. In fact, I think Hershey Park is Six Flags as well.
Yeah,
It was called Great America.
there you go. We have one.
Great
up there.
America. Great America. Anyways, Hershey Park in Pennsylvania contains some of the most famous roller coasters in the eastern United States. This scatter plot shows a relationship between track length in feet and the ride time in seconds for the 11 roller coasters in Hershey Park. Circle the dot that represents the roller coaster that you think is the most terrifying ride. Now, it's very subjective what terrifying means. Personally, failing a math class is terrifying. Roller coasters are not so much. Okay, so terrifying, what does that mean? So I have my own personal opinion here of what is the most terrifying. But what do you guys think? And then yesterday in my other class, we had some different opinions about which one was the most terrifying, but we came to an agreement at the end. And it was, of course, what I said.
I think track length, because there's that many more opportunities to give like craziness to it.
That's true. Okay, so the longest track length is automatically the most terrifying? What do
The
you say?
chances of it being,
Well, not chances. I'm asking which one, based upon these data points, is the
based on
most
this one?
terrifying?
the one with the ride time.
Which ride time? So which dot? There's 11 dots in that picture. By the way, notice that they're all the same color. This is not a categorical variable inclusive scatter plot, right? This is just the quantitative. So which of those 11 dots would you point to with your finger and say, that one is the one that I don't want to go on?
The very top.
Okay,
Yeah.
so let's look at the very top. What is the length for the very top?
3,000,
About 3,000 feet. And how long was that ride?
170 seconds.
Okay, so that's about 3 minutes, right?
Yeah.
So that goes a pretty good distance, but it also takes a kind of a while to do it. Right?
What does the shorter ride time mean it's faster though?
So the shorter ride time means it's a faster ride, correct?
Yeah.
So which one travels the
bottom right.
furthest in the shortest amount of time?
Oh, yeah, the bottom right.
The bottom right, right? The bottom one goes 3,700 feet in a minute versus 3,000 feet or something in 3 minutes. Right, David, you see that?
Yeah. I'm writing it
so
down.
in my mind, I think the bottom right is the most challenging, and that's the most terrifying. Sorry, this one right here. Okay, that one is the most terrifying. What is and this, by the way, it's called the Sky Rush. So what is the track length for Sky Rush?
3,700 feet.
About 3,700 feet. And what is the time for Sky Rush?
About 68.
Wow, look how exact you are. Okay.
Well, I don't know.
Let's say 60. Actually, it looks like 62 seconds, maybe. So that goes pretty far in not a lot of time. That's a pretty terrifying ride.
They should be measuring is the time you spend sitting on in line.
There is that. And there also could be, for some people, they're afraid of heights, and it's how high it goes. For some people, it's the biggest drop. For some people,
How many curly cues? How many backwards? How many upside down?
Right.
Yeah.
So it's certainly
That's why I was saying the length has that many more options to do that many more crazy things.
That's
I
true.
don't know.
But this one is not only the longest,
It's the
but it's
fastest.
also the fastest.
Got it. Okay.
So what is the relationship between track length and ride time based upon this scatter plot?
The fastest.
Well, we're looking for a relationship between all the 11 dots, kind of like the last few examples that we looked at. We want to look at an overall trend. Do we see linear, non-linear? Do we see positive, negative? Is it strong? Is it moderate? Is it weak? All these things that we're talking about. What do we see here? Come on, Angela, pipe in. You're quiet today. What's going on? We're missing your contributions.
I think Lori has plenty of good ideas.
Lori does have some good ideas.
That's what I'm saying.
Thanks.
So
Thanks, but I fake it till I make it.
So our Pine said there isn't one, and that's really my thoughts as well. I really don't see a relationship here. I just see a lot of dots. But again, my eyes can deceive me.
But why did you say that, Arpine?
because she looked,
Because
I don't know.
because it doesn't really like make a straight line. Like it doesn't matter if it's faster and the like it doesn't correlate with each other.
Got it. Makes sense.
Yeah.
It's like a circular blob of points. Now, of course, if I was really, truly interested in whether it was linear or not, I would calculate the numerical quantity that we're going to talk about in a few minutes. But we haven't learned how to do that yet. So this is a very qualitative, just eye-gazing guesstimate. And my guesstimate, like Arpine's, is that there is no relationship here. Okay, so let's move on to the next slide. All right, to study the factors that affect student success, CSUN conducted a study of the high schools that send 25 or more students to CSUN per year. For these high schools, is there a relationship between the average SAT verbal scores of entering CSUN students and the percentage who get a grant or scholarship? So just by looking at this scatter plot, would you say that there is or is not a relationship between the two quantitative variables given, the one on the x-axis and the one on the y-axis?
Wow, they're going in, aren't they?
Who? What happened?
The stats, they're going in.
Yes,
on picking apart.
Yeah, we are now getting into the good stuff. So does there look like there is a relationship between these two quantitative variables? We're all looking at the same plot. So basically,
seems like the lower the SAT score, the more percent with grants of scholarship.
It certainly looks that way, right? So we have a negative, we have a decreasing relationship because as one goes up, the other one goes down. Do you see that? As you move further to the right, as the percent with grants or scholarships goes up, then you go down, the average SAT score drops. Does that make sense? That yes. As the average SAT score goes down, the number of people or the percent of people who get grants or scholarships goes up. So there is a negative linear trend here. In fact, they were very nice and they drew the line through it. It's fairly strong, I think. As we're going to see later, there's this value here listed on the bottom left, the R squared value. And we have an R squared value of 0.8222. And as we're going to see later, that R squared value indicates a strong relationship between these two quantitative variables. Okay, so it is fairly strong.
Professor?
Now, yes.
Oh, sorry to interrupt you. So okay. With the terms that it's giving us at the bottom of the first part, it says strength, strong, moderate, or weak. How do you determine whether it's strong, moderate, or weak?
So we're going to have cutoffs. We're going to have numerical cutoffs that are going to tell us whether it's strong, moderate, or weak, or whether it varies. Maybe it's strong in one spot and moderate somewhere else, and so on. Although those are a lot harder to really quantify. But you're right. At this point, it's merely an intuitive guess based upon the graph. We don't at this stage yet have a numerical spectrum, which can say from here to here it's strong, and from here to here it's moderate, and from here to here it's weak, and from here to here it's non-existent. We don't have that yet.
So based on the graph that we have right now, because of how tight it is to being a line, would that make it strong?
Yes, that's exactly it.
And the more it dissolves into a blob,
exactly.
That's what it means by moderate or weak?
Well, once it reaches a blob, it's already non-existent, right? At this point, we don't have a line anymore. But if we go up to this one here, so this is perfectly strong, right? You can't get any stronger than that, right? It's perfect.
Right.
This is still strong. Once we're here, it's already getting moderate, right? Once it's here, this is probably still moderate. This is already kind of weak. Right, it's very, I mean, if you have to struggle to see the line, it's weak.
Got it.
And if you don't even see the line, it's basically non-existent.
All right, perfect. Thank you so
Right.
much, Professor.
You're welcome. And if you kind of see it, but it's like, well, you know, it can be tighter, that's probably going to be moderate. Okay, so we have strong, we have decreasing. Is it linear? Is it curved? Is it neither?
Linear?
It looks linear. There's a line through it. In fact, we've already established that it's strong. And the next question, are there any outliers?
Yes, the one that is near the 90%. 90%?
This one here?
Yeah.
Well, it's very close to the line.
But close to the line, yeah.
Oh, okay.
Right? I mean, basically, the only ones that might be outliers are the ones that kind of are really far from the line, but I'm not even sure I would call those outliers. I mean, they're not so far out that it's like if there was a point down here, I'd be like, what is that point doing there? Right? That point does not jive with this problem, right? Okay, if I was a point down here, I'd say, my God, that's an outlier. But these guys, I don't know if they're outliers. I mean, they're close to the line, a little bit off, but you know, not so far off that I think it'd be crazy, right? Yes, no, maybe so.
Correct.
You're not a talkative bunch, but I love you guys anyway. Okay, so
Yes, that is true.
all right, thanks. Okay.
Thanks,
We're
Angela.
letting you teach. We're letting you teach.
Oh, thank you so much. You guys are so sweet. Oh my God, I really appreciate that. And don't believe you for a second. Okay, so the correlation. The correlation is the strength of a linear trend. How strong it is. This is that numerical quantity that I've been alluding to for a few minutes now. How strong is the linear trend? So first, we have this numerical value, which we're going to see in a minute, called the correlation coefficients. I'm underlining it right here, the correlation coefficients. And its symbol is R. R is what is traditionally used for the correlation coefficients. And R is always between -1 and 1. You can prove that, but the proof is beyond the level of this course. So you will have to trust me, which when I teach math, I always tell my students, never trust me, verify everything. But in this case, you really do have to trust me because the proof is beyond the level of this class. Okay, but the correlation coefficient is always between -1 and 1. If it's 1, that's perfectly linear with a positive relationship. If it's -1, it's perfectly linear with a negative relationship. And all the numbers in between are going to be, if you look at the spectrum from -1 to 1, here's -1, here's 0, and here's 1. So these are perfectly linear with a negative relationship, perfectly linear with a positive relationship. Then we have the strong ones that are close to 1 or -1. Then you have the moderate ones, which are not as close. Then you have the weak ones, which are further away. And then, of course, you have the non-existent, which is very near 0. So if you have a correlation coefficient near 0, it's essentially non-existent. There's no linear relationship here. And as you move further from 0 in either direction, it becomes weak, it becomes moderate, it becomes strong, and then it becomes perfectly linear. So if you have a blob of points and you're like, what is that? That's nothing, then the correlation coefficient is most probably near 0. Now, a little warning here. When we talk about correlation coefficients, we are always, always, always focusing on the linear relationship between them. It is possible for there to be a different relationship that the correlation coefficient will not pick up. Okay? It could be non-linearly correlated, and the correlation coefficient will give you a value that you look at and you will come to the wrong conclusions. You can only trust the correlation coefficient if you have a reason to believe that the data is linear. Okay. I've seen plots of data with R values near 1 and -1 that are distinctly not linear. They are curved, but the dots are arranged in such a way that the math just gives you a value near 1 or -1. So be aware of that. The first thing I always recommend you do before you do any math is graphing. Have a graph of the data And then if you decide, oh yeah, I believe this data is linear, then go ahead and compute the correlation coefficient. Okay. Now, here's an example of ice cream consumption. The x-axis, we have the temperature, degrees Fahrenheit. And then in the y-axis, we have how many pints per person. Now, personally, I'm the kind of person who would be up here for any temperature. Okay, but that's just me. I'm an outlier, always have been. Okay, and these are averages anyways. Okay, so do you believe, forget about this line for a second. Let's pretend the line's not there. Do you believe, based upon the data, that between 20 degrees and 80 degrees Fahrenheit, that we have a linear relationship between temperature and how many pints a person eats of ice cream?
Most definitely.
Most definitely. Okay, once we've established that we believe we have a linear relationship, then it comes time to figuring out the correlation coefficient. Now, again, there's a mathematical way of doing it. This is a different question. This is multiple choice. I am listing here 5 possibilities for the correlation coefficients, and I want you to decide which of these is the correct one. So before you just shout out the answer, because I know you all have it, which 2 of these is it definitely not going to be of
the negative numbers?
The negative numbers, because negative numbers indicate a negative slope. And looking at this trend line, we definitely see that it goes up as we move left to right. Right, Angela?
Crickets.
Wow.
Absolutely.
Okay.
Sorry, I was trying to type an answer in the chat box.
I believe you. I do. I don't really. Okay, so now the question is.
I was going to put 0.9.
You were going to put 0.9. That one?
Yes.
Well, I agree with you.
Would you like me to explain?
Yeah, I would love for you to explain. That way everyone can hear why.
So I know it's not negative, so we crossed out the other 2.
Right.
It can't be 0. And if you compare, 0.2 would be not a strong correlation. So that would be much more scattered, while 0.9 is much more linear. So I can educate my guests because my professor has informed me it is 0.9.
Wow. That was so eloquently put. But I do want to say that that was an amazing explanation, and I probably couldn't do better myself. So that was awesome. So now I'm going to give you guys a couple minutes here. We have 5 scatter plots, and there's 5 correlation coefficients. Each one of these corresponds to one of the scatter plots, A, B, C, D, E. So what I would like you to do, and I will give you, you should need more than 30 seconds for this. I would like you to ascertain your opinion as to which number corresponds to which of these scatter plots. So I will give you just a few minutes to do that. Of course, keep in mind that without doing the math, it's impossible to know for certain what they are. So we're just kind of getting an intuitive guess based upon how it appears and what it should be. Angela, you're ready to share this one? You typed it before, or did you just type that just now?
No, I typed it just now.
So you want to go again?
Oh, I'm ready to go.
I'd take it down. What do you got?
Okay, so I would say A is going to be, negative 0.5.
A is which one? I'm sorry, you cut out.
Negative 0.5.
So A is negative 0.5, okay.
B is 0.5.
Okay, B is 0.5.
E is 0.95.
I'm sorry,
Or,
E,
sorry,
you said,
I read the wrong thing. I'm
Yeah.
sorry. C is 0.95. D is 0, and E is negative 0.95.
and E is,
Negative. I'd like to thank all my classmates for helping me with that one.
yes, they all gave you vibes that were helping you out, and they're giving you amazing comments in the link because Angela, that was awesome. That was perfect. I love it. Let's explain why. So this one looks like a blob of points. I see no linear pattern whatsoever. So that's the 0. Then 2 of them have positive slopes, and it just depends on which one you feel is the stronger positive one. So C looks much more tightly packed than B. So that C will be the 0.95 and B will be the 0.5, and similarly for A and E. So are there any questions on that? Because again, we haven't learned a formula for calculating R. All we have is rough ideas of what R should be. Okay, what we're going to do now for this problem is actually calculate it, which is going to be so much fun. But before we do, let's take a look at what it says. So it says computing and interpreting the correlation R. So the Algebra 1 Common Core standard is as follows. You have to compute using technology, and then you have to interpret the correlation coefficient of a linear fit. So here what we have is a scatter plot relating heights versus arm spans in centimeters of a group of individuals, most probably people, I would think, at these heights and these arm spans. Would you say, first and foremost, that this data is linear in nature? Would you say it's linear or nonlinear?
Linear.
Okay, linear. Once you've established that it's linear, now the question is which one of these correlation coefficients is correct? And we're going to confirm it on the calculator, but let's first get rid of the ones that we know are not correct. Which ones can we toss out?
All the negatives.
All right. Oh, I heard you, David. All the negatives are out. Okay. Can we toss out 0?
Yes.
Yes, because remember 0 means you don't see any linear pattern, and we certainly see one here. What about 1? Is this a perfectly linear relationship?
No.
Okay, so 1's out as well. So then what we have here is weak, moderate, or strong. And the question is, what do we think this is? Weak, moderate, or strong?
Moderate.
So you think it's moderate. All right. Would that be somewhere in the vicinity of a best fit line? What do you guys think?
Looks good.
Yeah, I mean, listen, you know, Gauss might be rolling over in his grave right now, but I think it's pretty good. Anyone get that? Anyone know who Gauss is?
I remember my algebra teacher talking about.
Yeah, what did your algebra teacher say about him?
I can't remember.
Oh, I guess it wasn't that important. All right.
Well, it was important, but I was trying to learn everything else.
I understand. There's only so much you can learn. So Gauss is arguably the greatest mathematician of all time. Definitely ranks up there. And as far as I'm aware, I think he was the first one to really, and Professor Dye would know if I'm not correct on this, but I think he was the first one, or at least the first one who published on best fit lines. Is that correct, Professor Dye?
I have no idea.
Okay.
No.
Never mind.
With multivariable best fit lines, I don't know. You know,
I don't know either. Yeah, I know he used a best fit line to predict the path of an asteroid or of a moon or something like that. And I think that was the first occurrence that I know of. But I don't know. I could be completely off. But either way, he's a great person, and you guys should emulate him in every way possible. All right. So the question is, does this data? Would you say the data is weak? Let's start with that one. What do you think it's weak?
I don't think there's that many that are not so close to the line, but I don't know. Maybe I'm just looking at it. I don't know. It could be wrong.
It could be wrong. Okay, so here's what we're going to do. We are going to go ahead, and I know that you don't all have a TI-84 calculator, but I'm going to go ahead and show you on the TI-84 calculator how to do this. So the first thing I do is I hit my stat button right here. If you have the TI-84 calculator, you can follow at home. I hit my stat button. And when I hit my stat button, you'll see the following screen. And this is on, of course, being recorded, so you can follow it later if you want. And when you hit the stat button, you see edit, you can see calc, and you have tests. So I'm going to go and hit the edit button, because what we're doing right now is we are editing. We are putting in our data. And what you'll see here is that we have 5 columns. I'm only going to use the first 2 because I only need 2 variables here. And my first column is going to be my x values, which are the heights. So 162, 184, 173, 181, 162, 175, 192, and 192. So I just went ahead and I put in all of my X values. That's the second column, okay? Because the second column is my horizontal axis. And then I go to the next column and I put in all the Y values, 161, 196, 177, 188, 159, 178, 194, and finally 188. And I have all of my X values put in as well.
So you put the same numbers down for those two columns?
Well, the first column will be my X values and my second column is my Y values, making sure, of course, that they're paired. Okay.
Yeah, no, I understand that. I just, why you put it in twice in L1 and L2?
Oh, L1 is my X column and then L2 is my Y column because I have two axes here.
So why did you put 161 on your Y?
Because if you look at the graph on the computer, arm span is the Y axis.
Okay.
And therefore, the 161 is an arm span, right?
Okay.
It's in my arm span data.
Show it again.
Okay. You're so demanding, you'll do it anyway.
Okay, I see what you did. So L1 is Y and L2 is X.
Just the opposite. L1 is X and L2 is Y. I know it's a little confusing because on the computer, arm span is listed first. But in my calculator, I flip them because I have X before. Okay. And then what I do is I hit stat again. I go back to this screen, I hit stat again. And then I go to the right to calc. I'm going to calculate something. So I go right to calc. And until now in this semester, we've been focusing on one variable stats, but now we're going to do two variable stats. But I'm going to go down actually to the fourth line, and it's called the lin-reg line, lin-reg. And I'm going to hit enter, and I'm going to hit enter, and hit enter, and hit enter, and hit enter, and hit enter. And eventually I get this screen. And what is the last line there? Someone read it to me, please.
0.93.
Oh, don't skip. Start at the beginning of the line.
R equals 0.93085,419.
That's right. So R equals 0.93 approximately. And therefore, that is the linear correlation coefficient for this data, which just shows you, Lori, that you can't trust your eyes. Your eyes might say one thing or think one thing, but do the math.
Yes,
math
trust
don't
the
lie.
science. And trust the science.
And trust the math, trust the science. Okay, excellent. All right. Now, of course, we want to interpret the value of R. What does it mean that R is 0.93? It doesn't mean 93%. Okay, does not mean that at all. If you want to interpret R, here's what you do. And this is a little advanced. If you don't get it, it's not the end of the world. I'll try to explain it, but it is a little advanced. So what we do is we square R. We take the 0.93 and we square it. So when I go to my calculator and I do 0.93 squared, I get approximately 86.5%, 0.865. Now, the R value just tells me how linear it is. But the R squared value actually has a pretty nice physical interpretation. And that's as follows. Go back to your graph for a second and look at all these points. How many points do we have? 1, 2, 3, we have 8 points, right? Do those points all have the same Y value? Do all 8 points have the same Y value?
No.
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 Give me a reason why they have different Y values.
Because
Yeah,
everybody's.
different.
Oh, go ahead.
Go, Lori.
I was just going to say they have different measurements of arm spans.
No, I understand. So give me a reason why they have different measurements of arm spans. Why do two people, if I look at two people and I say, hey, you guys don't have the same arm span, give me a reason why that might be the case. Why are their Y values not equal? Give me a reason for that. I can think of 2 reasons right off the bat.
Paralyzed?
Wow, okay, that's kind of going a little hardcore there. So my 2 reasons are as follows. First of all,
Adults or kids? Huh.
well, yeah, they don't all have the same heights. Why would you expect them to have the same arm spans? Why would you expect someone who's got 193 centimeter height to have the same arm span as someone at 162 centimeters? right? The reason, the number one reason why their y values are different is because their x values are different. Different x values give you different y values. If I were to make a line here, my best fit line, or at least approximately so, why is it that x values here are down around here and x values here are up around here? Because we have a linear trend. We expect that as the x values go up, the y values go up, right? Does that seem reasonable?
Yeah.
But how do you explain these two though? Because these two have the same x value, and yet they still have different y values. So your first answer is, well, bigger x, bigger y. Yeah, I agree with that totally. But wait a second. Same x, different y? What could be the reason for that? And the answer is because life is imperfect. Just because two people are the same height, they're not going to have the same arm span, right? Genetics, nutrition, whatever, right? People are going to have different heights if they have different, different arm spans, right? Yes, no, everyone, everyone?
Right, we're all different.
We're all different. So the reason why the y values are different can be attributed to two different things. One, different x values, and the other, that's just life, right? Life comes with variation. This value here, this r squared value.
Do you want to officially report it as missing?
Yes, yes.
Officially?
Yeah, yeah.
Okay.
This r squared value over here explains how much of the change or variation in y can be explained because of the variation in x. 86.5% of the reason why the y values are different is because the x values are different. And the other 13.5%, that's just the variability that's inherent in life. Okay, this is a explanation for r, or at least r squared. And if you go back to that graph above that actually had an r squared value listed.
Yeah, it's 0.866.
0.822, right? R squared is 0.822.
Yeah, yeah.
So this is saying 82%, so 82.2% of the reason why the y values are different is because the x values are different. It's because of the linear trends. And the other 17.8%, that's due to variation in life. So the stronger the correlation, the more perfect linear it is. If I look at this one right here, this r value is 1. Its r squared value, therefore, is also 1. And therefore, 100% of the reason why the y changes is because x changes. And there's no variation. There's no, hey, real life happens. Not in this case, whatever this magical situation is. Okay, if you can find one, I'd be really impressed to see it. In real life, there's almost, I can't even think off the top of my head of a situation that has no variation. In math class, you know, hey, yeah, you have a line. That's perfect. But in real life always comes with variation. Now, in the last example, we dealt with the correlation between these two lengths, and we focused our attention on centimeters, right? Both of them were written in centimeters. What if I were to go ahead instead and measure them in inches? What if I were to go ahead instead of centimeters, if I were to measure them in inches? Would the correlation change? Look at all these numbers. Do I think the correlation would change when I change centimeters to inches? So first they're saying, well, first fill in the blank. I lost my data. I had my original data. I had my new data, but I don't know, I spilled something and this got erased. And what value is this? How do I find what the 177 corresponds to? How do I find that number? I have the relationship between inches and centimeters, and I have how many centimeters. So how do I calculate how many inches? Who here knows?
You divide your original data by 2.54. So basically 177 by 2.54.
Yes, but can you explain why that works?
No.
So here's the reason why. We have that 1 inch, or better yet, 2.54 centimeters. 2.54 centimeters is to 1 inch. This is the same ratio as 177 centimeters is to our unknown amount of inches. So we have this mathematical equation, 2.54 over 1 equals 177 over x, if we don't worry about the units. And then how do you solve a situation when you have two fractions that are equal? You cross multiply. So 2.54 times x equals 177 times 1, or just 177. And then Yesenia, what's the last step?
You divide?
You divide by what?
2.54.
On both sides. So 177 over 2.54. So you went right to the answer and you were correct. It is 177 over 2.54, but it's always better to understand why that's the answer so that we can extrapolate to new situations. And we get 69.6.
Yeah.
Right, 69.7. And if I were to go ahead, and just for the interest of time, if I were to go ahead and plug these into my calculator instead, what do you think my R value would be? The answer, 0.93. Because correlation is deeper than units. Correlation does not care about the units. If you change the units in a consistent manner, you will get the same correlation coefficient. Okay, because at the end of the day, we have the following. I want to show you some graphs here. Let me first get rid of these so it clears it up a little bit. Okay, so look at these 4 graphs. All 4 of these graphs are measuring the same thing, height versus arm span. This one is centimeters versus centimeters. Then we have inches versus inches, inches versus centimeters, centimeters versus inches. All 4 possibilities. What do you notice about the appearance of all 4 of these graphs?
Everything looks about the same.
They look exactly the same. Of course, the scales are a little different, but they look exactly the same. And mathematically, when you go through the math and you compute it, you get the same value. The math is not particularly difficult to go through to show this. However, I would have to introduce the equation, and that is daunting. That's one of those things that you see and you just start crying, right? It's kind of like me in the mirror every morning. So, you know, we're not going to do it, but just trust me on this one. Trust me on this one, that the correlation coefficient does not depend upon units. Not only that, we could even go ahead and switch X and Y. Forget about the units. I can completely switch the X and Y axes and I'll still get the same correlation coefficient.
Can you explain the, it says, yeah, so it doesn't affect that. And can you explain that again? Because, yeah.
Yeah, does
changing the units
of measurement affect the correlation? The answer is no.
No, but the explanation is because
Correlation.
So the explanation, I guess a good explanation at this level would be something along the lines of,
oh, is that what you were saying? Just trust me on this?
Well, no. I mean, you can trust me that it's true, and you can trust me that the math gives it. But as an explanation, I mean, when you're determining the correlation between two things,
it's still like the same formula or whatever, right?
You're comparing the same objects, right? Okay, whether or not you measure those two objects in different units, they're really the same objects, correct?
Yeah.
And as such, the units that you use to measure it doesn't change the fact that the things that you're comparing have a certain relationship between them.
Okay.
Right? And the units just help us quantify that, but the relationship exists either way. Okay? And when you change X and Y, it also does not affect the correlation. Again, in the interest of time, I'm not going to just show you, but
sure,
you can trust me on this one. And again, because correlation is about whether or not they're connected. And when you talk about connection, X is connected to Y just as much as Y is connected to X. It's the same relationship, just looked at from the reverse perspective.
Okay.
But you're not changing how strong that relationship is. Okay. Now, outliers. We've kind of focused mostly so far on strength, form, linear or not, how strong it is, and positive or negative. The fourth of the big four, this is outliers. Okay, and you can have an outlier that's there's really four possibilities for an outlier. Possibility one is it's an outlier in the x direction, but not the y. Or next one, the y, but not the x. In other words, it's an outlier in one variable, but not the other. Which one? Well, it could be x or it could be y. So technically that's two possibilities. Okay. The next one is it's an outlier for both variables. Okay. In other words, either x or y, either way, it's an outlier. The last one is it's not an outlier for either variable. If you look just at the x's, nah, not an outlier. If you look just at the y, not an outlier. But when you look at them together, it is an outlier. And we're going to have a picture on the next page. And that picture on the next page is going to demonstrate all four of these types. Okay. So again, it could be an outlier for the x, but not the y. It could be an outlier for the y, but not the x. It could be an outlier for both x and y, or it can be an outlier for neither unless you look at them together. So the scatter plot on the next page gives the weight in pounds and the length in inches of a large sample of black bears. For each point, A to E, tell which type of outlier it is and then describe the bear. Before we do that, this reminds me of my favorite riddle. I'll take a minute to do this because it's really a fun riddle. But if you know the answer, you can't say anything. So, Landra, you paying attention? This is an important riddle. Okay, so here's the question. Ready? Everyone here? Say yes if you're here.
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 Yes.
Okay.
Here.
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 So here's the riddle.
Here.
Listen very closely.
Here.
Okay, I got it. You're all here. That's fantastic. Okay, here's the riddle. A man leaves his house and travels 1 mile south. He then travels 1 mile east and then 1 mile north, arriving back at his house. A bear approaches. What color is the bear?
Doesn't matter. Nothing is real. We live in a simulation.
Wow. Okay. So that's going very matrixy, but nevertheless, for those of us who still believe this is a real universe, a man leaves his house, goes 1 mile south, 1 mile east, 1 mile north, and he arrives back at his house. A bear approaches. What color is the bear? Come on, hurry up. 30 seconds. Who knows the answer to the riddle?
I would say there's no correlation between the two, and you don't know.
Anyone? What color?
I don't get the correlation.
No, this isn't about correlation. This is a riddle. This is a kid's riddle. Don't. Why, Wendy? Why is it white?
Oh.
Why is it white? Hurry, hurry. We have math to do. Why is it white?
I don't know. I was guessing.
It's a white because it's a polar bear.
Oh.
The only way you can go, well, not the only way, but pretty much the only way you can go south a mile, east a mile, and then north a mile and arrive back at where you started if you were at the North Pole.
I didn't know that. I was just gonna guess.
Oh,
Until I
well.
got it right.
You guys all failed. Okay. That's my favorite riddle, and you guys all failed.
At
Anyways,
least it's not an IQ test.
Well, I just lost about 5 minutes.
Wow, thanks so much. First of all, it was only 2. That's first of all. Angela, take that back. Take that back. That's an awesome riddle. And you're all going to use that riddle, by the way. You know you will. You know you will. So, all right. So here we have all of our black bears. We have a scatter plot. Here is the length in inches, and here is the weight in pounds. And there's 5 outliers: A, B, C, D, and E. Okay. And oh, Crystal, that hurts. And what we're gonna do is we are going to figure out what kind of outlier A, B, C, D, and E all are. So let's start with A. So let's start with A. Would you say A? Oh, actually, let's do A last. I changed my mind. Let's do A last. Let's start with B. Does black bear B have a length that is strange compared to the grouping of all the black bears? Is its length in inches irregular?
No, it's weight.
Well, one second. Is its length irregular?
No.
No. Is its weight irregular?
Yes.
Yeah.
Yes. Okay, so black bear B is an outlier for weight, but not for length. Its length is
Right.
perfectly normal.
One
Right,
berry.
right. It's right here at 75. Lots of them are at 75, but its weight is abnormal. What about D? Is D actually, let's do D again later. Let's do C. Is C abnormal when it comes to weight?
No.
Is it abnormal when it comes to length?
Yes.
Yes. So C is an outlier when it comes to length. Let's now look at E. Is E abnormal when it comes to weight?
Yes.
How about length?
Yes.
Yes, so E is both. And now let's look at A and D. Is A abnormal when it comes to length? Is its length? No. How about weight?
Not really.
No, because there's lots of them that have the same weight and lots of them that have the same length, right?
Uh-huh.
But when you look at them together, weight and length, now it becomes an outlier. And D is similar, right? D has a perfectly normal length, a perfectly normal weight, but it's only when you look at them together that it becomes an outlier.
Wait, Professor, what did you put for A?
A is a joint.
Oh, joint.
Joint or jointly outliered.
Okay.
Okay. So does that make sense for the various four types? And how do I
It's
identify
different
them?
between jointly and both again. I missed something there.
Both means that it's an outlier when it comes to length. It's an outlier when it comes to weight. It's an outlier for both. Even if you didn't have the other one, it would still be an outlier. Joint means it's only an outlier when you look at them together. Okay, either one individually would not be an outlier. But when you look at them together, it becomes an outlier.
Okay.
So
When
what
you look
about-
at the points together.
Just 1 point. If you look at point A right here, it's got a perfectly valid length. It's got a perfectly valid weight. But that length and weight together, that now is very strange.
Okay.
Okay, same thing with D. Perfectly valid, but together, a bear like that is very irregular.
So C was because of length.
Right, C is a perfectly valid weight, 400 pounds. Lots of bears have 400 pounds.
Yeah, but it's not hitting that 400-pound line.
Well,
That's what I'm saying.
it's at 400, right? Right,
Okay.
C is about 400, right? Maybe
Yeah.
at 390, whatever, but around 400, right?
Yeah.
So it's not the weight that's making this irregular. It's the fact that it's really, really, really long, right? And B is the opposite. It's not long. It's 75 inches. Lots of them are 75 inches, right? But
Okay,
its
it's heavy.
its weight is 600 pounds. That's crazy. Okay. Okay. So I don't want to leave without saying this because this is extremely important. It's a difference between association and causation. Okay. Just because two variables are associated, because they are connected, does not mean they are does not mean that one causes the other. In fact, do you guys know that if you look at children from, let's say, 5 to 13, let's say, if you look at children from 5 to 13, do you know that the ones with bigger feet are better at reading?
Yay.
Okay.
Good to know.
Why would it be that kids with bigger feet from 5 to 13 are better at reading?
Because they're older.
Because they're older. That's why they have bigger feet, right? I'm not looking at only 5-year-olds. In that case, I would think that there's no correlation between reading level and foot size. But if you look at a wider range, there could be a variable lurking behind the scenes, a lurking variable. A lurking variable is one that you're not really investigating. It's lurking behind the scenes, and perhaps that's really what's going on behind the scenes. So just because things are correlated does not automatically mean that they are, that there's a causation, that one causes the other, okay? Even without my lovely riddle, we'd still not quite finish today. So we didn't finish 15. We're gonna finish this next time before moving on. Actually, next time I believe we're reviewing for the exam, right? The exam is Thursday, and we are going to review for it, and then you all have, and then I'll post it, and then we're going to continue with this material next week. So, are there any questions on anything we did today?
No, I just have a, I have a quick
anyone like the
question.
Berkowitz Book of Riddles, because it's full of great stuff, huh? You have a question? What was your question?
Yeah, I do. I have a question. So for Thursday, you're gonna post the exam, and when will that be due?
So the exam, so you'll have the weekend to do the exam.
Okay.
It'll be due before class
On Monday. I mean,
yeah, because my other class is taking it too. So you both
Right.
have to have the same amount of time. So their class is Monday. You will have the
Okay.
weekend to do it. Okay.
Thank you.
Okay. Any other questions before we call it for the day? Well then, as always, it's been a pleasure. I'm going to stop recording now.